Hello, welcome. My name is Veldboom, and this is another Veldboom Studios video. It's been a while since I've done actually like a full tutorial on how to design something and also the things that I'm working on. First and foremost, what we need to do is actually go to SolidWorks for makers. So just Google that. Let's see. Oh, there's actually like a 50% off at the moment. So if you do it right now, it's even cheaper. I think it's going to be like 30 euros or something for a year. And then you have two versions that you could download. And this is like a cloud app version. If you have like a Mac or something, then that could be good enough already. But I would definitely recommend having a Windows computer to do SolidWorks on. And then also going for this package so you can actually download the whole system and everything to your computer locally. So as soon as you fully download everything and got the subscription, then you will be sent towards this page. So save it somewhere because it's kind of hard to find it sometimes if you don't have like the link or anything saved. So that is basically what I would recommend you to do. And then here you will have like the design tools and collaborate and manage. So also if you have it in collaboration with other people, you can start to share files and everything. I haven't really gotten into that because I don't really have like a lot of people to kind of collaborate with. But I'm very curious to see what everything like the 3D experience and the SolidWorks makers kind of has to offer. So then the SolidWorks Connected, that is the one that you need to download. So I already did that. So for me, it says open, but for you, it will say install. So please do that. And then you'll be you can then click on open as soon as it is installed. So basically today, we're going to make something very similar to this, but I'm just going to make it a little bit more complicated. I'm going to go through it a little bit quickly, but still, I'm going to just describe everything that I do. And if I'm going too quickly, you can just look at all of the moves that I'm making and also play it maybe back a little bit slower or something, but try to follow along. Like I also said in the previous video, don't make this like a complete carbon copy of what I'm making. If you want to make it your own, please go do that. So first and foremost, let's also go to ChatGPT. The first prompt that we're going to put into ChatGPT. So today we will be making a 2.5 liter ICE, so ICE means internal combustion engine, in SolidWorks makers. I want it to be a high revving, naturally aspirated engine with a very high efficiency. So I want you to act like an engineer slash MATLAB expert to help me decide on which dimensions I should use, and also to calculate the power output of the motor. That's step one. So here is the response from ChatGPT. Great, let's start using some design parameters and performance goals for your V6 engine. We'll be using key factors such as bore stroke, compression ratio, and valve configuration to guide the design process. Here's what you'll need to decide. Figure it out. So let's answer these questions first and foremost. So basically I said we want a high revving engine, so please make the bore larger than the stroke, but maintain the 2.5 liter volume, compression ratio of 13 for the power target, compression ratio of 13:1, but for the power target I want to let you calculate the outcome based on the inputs. Let's say max RPM at 12.5K with regular fuel. So now it kind of gave me all of the dimensions I need in order to maintain the bore and stroke and everything, but then with a 2.5 liter displacement. The max RPM is set to 1200, and then the estimated power output would be 934. And the reason why is that probably because it seems way higher than the 400 or 500 that I initially mentioned. But if you have like 12,000 RPM instead of like 7,000 or something, then you're probably just gonna double the amount of combustion strokes that you can put your engine through, and therefore damn near also doubling the amount of power that you can make out of a motor. So that is basically now the estimated power to weight ratio and everything that we would have with this compression. I'm also going to ask ChatGPT to give me all of the calculations needed. So here, for the people that are interested in how you can actually like calculate that whole power output of the motor, it's pretty, I'm not going to say it's simple because that's why I let ChatGPT do it. But so let's get into it. We're now actually into SolidWorks, and basically first I'm going to give you like a basic overview of the whole layout and everything, and show you where the tools are, what you can basically do with them. And then from that point forward, we're just going to move into it, and then you kind of just see as we progress like where everything is and how things go. So here you will see these tabs, and you'll have the feature tab, sketch, surface, markup, elevate, everything like that. Most of the things that we're going to use will be consisted of these three tabs right here. So feature, sketch, and surface. But here you have these, I think we customize. So here you can see that I've used the standard views. I've checked this one. That way you kind of get this selection right here. And to me, it's very handy if you just want to kind of like step through different positions, if you want to see like from which perspective you're watching your object from and stuff, you know. It's kind of like the way that I kind of do that. And then also here you see your feature tree, and that is going to be very important. This will be like a list of all of the actions and the features that you actually make in order to like accomplish your design. But then also they will be in a sequence where you can also change it and moderate it and stuff, where you know you can just be very flexible with also past changes that you've made. And that's what also separates this from Blender. It's not just, or like any like regular like modeling or something, that you can actually go back into different individual moves and change and make iterations to like sketches and dimensions and stuff like that. So that is basically what we'll be using. So first and foremost, we've already know a couple of things about the engine that we're gonna make, and that is like the piston bore size, which is the diameter basically of the piston itself. In order to make that, we're gonna select this top plane, and then we're gonna select sketch. And you can also basically start off by pressing like extrude boss base in the feature tree, but we're now just gonna start it off with the sketch one right here, and then we're gonna, from sketch, I'm gonna go I'm going through it too quick already. And so as soon as you press sketch, you have here like all of the line tools and the different like options of how you can make a sketch. But now first off, you're gonna start off with just drawing a circle. And you can already see like the R is 69.26 in screen. Like the dimensions will be like updated as soon as you kind of drop it down somewhere. But we actually have a very specific dimension that we want to give it. And the way that I actually kind of got here was by pressing smart dimensions, then highlighting the circle, and then you will kind of get to it. But then we also need to get to the power of ChatGPT again, and then we see that the bore is actually 86.3 millimeters. So I'm just gonna Control C, paste it right there, and now we have a bore of 86.03 millimeters. So for a piston, it's actually pretty simple what you need to do in order to transfer this into something that could be already used in the basic intro that I showed with the single engine piston block, you know. So we're just gonna extrude this circle sketch. And from this point forward, let's say we'll make it about 60 millimeters, I want to say. Seems about right. We can change that in a later stage. But this is like the basic principal shape of a cylinder that we would need in the correct dimensions as we have it already. So from the bottom, I want to also make a sketch again, because we also need to put a pin right through it. So we also need to have some surface area where we can actually like drill a hole through it, and then allow us to kind of connect it but still maintain surface area with the cylinder wall and everything. So what I usually end up doing is I take out the sketch tool again, but on this bottom surface. So let me exit it and show you again. As soon as you select a flat surface in SolidWorks, you can press the sketch tool again, and then we'll use that surface to sketch upon to create your next like design feature. And in this case, I want to draw a line that goes from the top to the bottom. I'm gonna place my camera a little bit more like this, and that is basically what's gonna allow us to then also like cut off the end caps basically. So here we have in the next step, so here you have all of the lines, and here you have like some ways to modify sketches that you've already made. So either you can convert entities, and that is like the tool that you can select other lines with, and kind of convert them into sketch drawings basically on that plane. So I could also select this one and it would still project it on a plane right there. And then offset entities is basically the tool that allows you to take a line that is already in existence, but then create like a slight offset to it for either one side or bidirectional. And in my case, I need it to be bidirectional. And then basically now you can see that a 30 millimeter offset on both directions is what we got. And I think for now that will be fine. And then once again, now that we have this sketch, I pressed extrude cut, and I can cut off these end caps. And I don't need to do that all the way through because we still need to maintain like a solid, basically a piston surface that don't like allow gases to just flow into the engine block. Um, but we also need it to be maybe like this, 45 millimeters, something in that region. Um, and that is basically like the first initial shape that we have to kind of make it recognizable as a piston. And then we also need to hollow it out from this bottom section, because basically right here is where the connecting rod will attach to it. And so again, we're gonna select this surface, and I could click on sketch and then click the sketch tab right there. But with the surface sketch, but with the surface actually selected, I could also directly click on extrude cut. Here you can see offset entities, and then I don't need it to be bidirectional. Let's say these walls will be 5 millimeters thick, something like that. Maybe let's say 10, maybe a little bit better. And then we can just basically cut this out again. And the previous cut we made was 45 millimeters, so it will just kind of keep that dimension. You can make this a little bit less like steep if you want to. It just depends on like at later stages how strong it will need to be, how lightweight you need it to be, all that type of stuff, you know. So now we have again selected this interior face surface, and we're now gonna make also the hole that the connecting rod will actually be able to put the pin for, also through the connecting rod, I should say. And we're gonna make like a diagonal line from this edge to the other one to find the middle just very easily. You could also do it straight line, but you know, it's just preferences, I guess. And I also like that a little bit about SolidWorks is that it's not just too binary. There are just multiple ways of going about it and doing stuff, you know, so just find whatever fits comfortable to you. And then for the actual pin for the connecting rod, let's say it should be about maybe 30 something millimeters, maybe 25 or something. I think that should be sufficient, something like that. And then to actually cut it, and then we select cut extrude again. I just select this line, and then instead of giving the dimensions where we need to cut extrude, you can select blind here and select through all both, and then it will just take the maximum outer dimensions that it should take in order to actually make the cut, you know. And this right here actually already is somewhat of a basic piston at the dimensions that we needed. And we're gonna make a whole bunch of more tweaks to it at later stages. We need to add like the compression rings and the oil rings and stuff like that to it, and there's a whole bunch more that you can do to it, but this is like the first step, I guess. So then what we need to do, very important, is actually save this component. So I'm gonna save this as the piston, and then that's basically done for the first component. We're gonna make it like a higher detail in other videos and stuff, but for now I just want to make it as fast as possible, a little bit rudimentary in the beginning, but we'll be fine. So for the next part, we're actually gonna make the connecting rod, and also for that we're gonna go back to ChatGPT, because we're also gonna ask it what would be the optimum length of the connecting rod from the position where it attaches to the crankshaft to the actual piston, because that's also a pretty important ratio. So what would be optimum connecting rod to stroke ratio? The connecting rod to stroke ratio is an important design parameter in engine performance. It affects engine durability, high RPM capability, and piston side loading, and overall efficiency. So just to highlight and to showcase why the connecting rod ratio is important, basically what it does is if you have a taller connecting rod, as you can see in the screen here, so if the distance between where it connects to the crankshaft and where it connects to the piston gets larger basically, then the angle at which it kind of pushes against the sidewall, so you can see here, as soon as this would move upward, it is kind of pushing that same, let me connect this to the interior wall to kind of keep it in position a little bit. It is basically pushing the piston against the side of the cylinder wall at an angle, and that angle gets less steep the longer that the connecting rod is, because it will just basically sit more perpendicular to or parallel to the cylinder wall in a way. So the longer you make it, it actually will produce way less friction. It will have less stresses, and also the duration will be longer on the engine because there's less friction, but you will make the rest of the whole entire engine just longer depending upon the ratio and the length of the connecting rod you'll use. So overall you would have like a very a more lightweight engine if you have like a smaller connecting rod, but it just goes for whatever ratios and things you want to use. So that is kind of like the base premise of why the connecting rod length is very important. So let's now go back to let's say to ChatGPT, and then we can find out what the optimal rod to stroke ratio would be. So here they're saying for a high RPM, 12,500 RPM, high efficiency, we want to reduce the friction and the piston wear while maintaining good combustion, and therefore we would go for a higher rod to stroke ratio. So in this case, that would mean 1.8 to 2. And given that the stroke is 71, we want to have a ratio of 1.9. I'm gonna just make it like, let's say, a ratio of 2. So then just double this value for the actual connecting rod ratio. You know what? Let's just listen to ChatGPT. I'm gonna keep it at 1.9, and then this would then be the length for the connecting rod ratio. Let's just keep it at that. So now we're gonna make part 2, and this will be the connecting rod. So now I'm gonna start with let's say front plane, and then we're gonna click on extrude boss base, and we're gonna draw a circle from the top. And we already know that the hole that is actually in the piston itself, where we want to connect the piston rod, is 25 millimeters in diameter. So that is going to be like the initial measurement. For the connecting rod, for the crankshaft, we also know that the stroke will be 71.69 millimeters. So this is where the pin for the connecting rod and the piston to be connected to each other will kind of go through. And then I'm gonna use, let's back that up a little bit. The outer dimension for this should be like 40 millimeters, I think, something in that ratio. And then from the center of the circle, I'm gonna draw a line down, and then this is gonna be the 136, the actual length of the connecting rod. Let's see, yeah, 136.21. And then we're gonna connect that to, let's say that the bottom lobe, this is basically where the connecting rod will connect to the crankshaft. I think this should be maybe about like 60 or something. And then we'll put that at like maybe 7.5 millimeters offset, something like that. And then also what we're gonna do is take this circle and make it bidirectional. Take this line, click offset entities, make it bidirectional right here by selecting it, and 10 millimeters should be good if it's like 2 centimeters at both sides. And then the final thing we're gonna do is basically draw a line down the bottom, and this is your basic sketch for your connecting rod. We're gonna make it a little bit more complicated in the future, but for now, these are like your basic proportions that you need. Okay. And then if you also want to make it a little bit stronger, make it look a little bit tougher, you can add some fillets to it in the corners or something. Kind of smoothing out a couple of the lines in here. And make it a little bit larger, something like that. But also it is way too thin. So I think it was like 30 millimeters or something in the actual piston that we left as a space. I think so. We'll check it out in a second if this would then actually fit. And then that would be the basic start of your connecting rod. So also let's make sure to save this. So that is now the second part completed of this first initial design draft of the motor that we're making. And now I'm gonna make the final component that we need before we actually put them together into like an assembly, and then we're also gonna make the engine block itself. And that is actually going to be the crankshaft. So we have a couple of dimensions already for it. So we're gonna select the front plane, extrude boss base, and I'm gonna start off with making a circle, which will actually be the axis that it is rotating in within the engine block. So I'm gonna put that at about I think 50 would be good though. And then we also know that the piston itself is about 86 millimeters wide. So let's say we're gonna start off with 100 millimeter length, I guess. And then the next dimension that we know is the actual stroke, and that is gonna be 71.69. And that is gonna be the axis of rotation of where the actual connecting rods will be attached to. That will basically dictate what those dimensions are. And we also know already that the connecting rod, the bottom section, the ends of those are, was it 30? What did I make those? Let's check it out. I think it's 30, but we're gonna find out real soon. Connecting rod. So that way you can also go back into your previous parts and do those measurements and stuff, you know. So you can see here it has a radius of 30 millimeters. So it actually is 60 millimeters wide, the diameter. So that's also why it's important to double check, because you know, sometimes you can get some stuff wrong. 60, there you go. And then from that point forward until basically, let's say here, so that would be like a 14 centimeter wide, about that 14 centimeter wide crankshaft. So in your files it might look a little bit large right now, but this will make complete and total sense in a moment. So okay, so we're gonna make it to where this is basically the outer dimension that we need. These sketches we're not gonna use at this very second, but we need them in order to kind of incorporate the rest and everything, you know. So let's also check this right here. Let's just put it at 70. Then we have like some square hole dimensions, I guess. And then we're gonna take this line right here, let's say 10 millimeters, and we're gonna make it in the other direction. So if it is kind of like looking into that direction, you can flip it around by hitting that switch. And then we're also gonna make it offset, because we don't want it to kind of protrude from this surface, but we kind of want it to go inward a little bit, and now it is offsetting into the wrong direction. So again, you can make it go into opposite direction, and about 10 millimeters should be sufficient in this manner. And then we're basically gonna do the same on the other side. Is to kind of, but then like I said, you can select this surface, click on the extrude, and we'll automatically start the sketch there. Then you can click on this surface, click on convert entities, and you automatically have the same sketch lined up right there. Then extrude again, flip it into the other direction. We don't want to select it from, we don't want to extrude it from the actual sketch plane where it's being sketched, but we wanted to offset it by 10 millimeters into the other direction, and boom, now we have this part right here. So that is the first part and the first stages of what it takes to kind of make a crankshaft. The next is to actually go into the surface again, click on extrude, but now go into this sketch that we made for the first one, and then you can kind of see where the other sketches and things are lining up. So we want to keep that sketch, but before we kind of continue on from that point, we first need to delete this middle section that we're keeping right here. So let's just go into extrude cut. We're gonna select like the entirety, and not select through all, but maybe select up to surface, select that other surface, and then it will leave you with two bodies. So then we'll kind of give you a window to select which one you want to keep, and in this case we want to keep all of it. Sometimes you can also select that one of them will become negligent if you just cut something off like that. So that's basically why they have that up in there. But then again, we will select this surface again, click on the initial sketch that we made for the connecting the crankshaft, and then go to boss extrude, select this outer line, go to boss extrude again, select this line here, go to up to surface, select this surface, and then we'll make it whole again. That's the basic premise of a crankshaft. You will have one part that is connected to like a center rotation axis, and then another one which will basically become the pivot of the connecting rod to be connected to, you know. So those are the first three components. I'm gonna save them. I'm gonna bring them together in an assembly. Crankshaft 71.69. for a single piston block. And then now we're going to actually bring them all into an assembly. So here we have the crankshaft, the connecting rod, file, new, assembly. And this for the first time we're now going to go into an assembly. And here you will see a slightly different setup with the tabs and everything. So instead of having feature, I think then it's sketch and then like some other stuff. Here you see assembly and then sketch, and then things will kind of change as soon as you also go into a part. So the very first thing that we want to do as soon as we start basically on this journey that we're on right now is the very first thing that you want to do as soon as you have like an assembly is to add some components to it. And in my case, I'm going to start off with the crankshaft. I think that should be like a little bit of the center, I guess, you know, so it makes sense to kind of keep it that way. And then insert components, let's add the connecting rod. And also insert components, it's not open anymore, but I can find it pretty easily, is the piston. And now we have these three components selected. And now it is basically our job to make them together again. And the way to do that is by selecting in the assembly tab, selecting mate. And with mate, you can basically select the surface, and if it notices that it is like a cylindrical surface, then it will kind of always find, or not always, if you then select mate and also select another cylindrical surface, then they will always form concentric circles where they're just enclosing each other. And that is like the first mechanism that you would need in order to kind of like fully make something, you know, shapeable that way. And that same process is basically going to be repeated throughout the engine block, because, you know, a lot of those shapes are kind of like concentric mates when it comes to pistons and crankshafts and stuff like that. And then here we can see that the couple of distances and things aren't like matching up perfectly, but we can still play around with it and also change it from there. And now for the final part that we're going to actually make in this tutorial, we need to make the engine block. And for a V6, it's going to be a little bit more complicated. That's why I also chose a V6, because we need to basically make it in a way where there's a slight offset. People might think that for a V8 or a V6 or something that you could just mirror what is on the left side to the right side, but there's going to be a slight offset because of the connecting rod position. Because in real life, if you actually have like a V engine, then we can also already kind of like select it and see how that is going to look. If you select the connecting rod, you can also see it being highlighted in the feature tree. So here in the assembly, you will also see like a whole outline of all of the parts that are within your assembly. And this line can be pretty substantial as soon as your assembly is kind of become more and more complicated. So now in this case, we're going to select the connecting rod again. I press Ctrl-C on the keyboard, and Ctrl-V, but just basically paste it. And then we can select it again. And then, so this is now the first step of actually starting to build also the engine block. But I'm gonna go back to ChatGPT one more time, because also when it comes to making a V6, there's also an angle that you need to take into consideration, and it is the angle that actually splits the banks. Because if you have a V8, then you would want it to be a 90-degree angle, but for a V6, I believe it should be 120 or 60. For a V12, it would be the same. And I think V12s are kind of like inherently imbalanced, because they depend upon which degree of angle you kind of choose to attack. In the rotation cycles, there will be like combustions happening at similar times at equal or opposite sides of the bank, enclosed or ensuring that the vibration load and everything through the engine will kind of be balanced in a way. So what I also want to ask ChatGPT is what would be the optimal bank degree. So ChatGPT basically says that for providing intervals which at 120 degrees of crank rotation, so for every third of a rotation that the crank makes, there will be a firing cylinder if you have the bank separated at 60 degrees. For a V8 engine, it will be more common that it is at a 90% degree angle or something, but we're basically going to go for a 60-degree split angle between the two banks. So that is basically saying that the ratio at which these pistons kind of go out on each other that was maintained at a 60-degree angle. So what we're gonna do first is actually not only select a new part within like SolidWorks itself, a new part, but we're actually gonna make a new part within this assembly itself. So select new part, and I'm gonna use this outer surface of the crankshaft to kind of start it, because I also want to use that as a dimension to kind of build the rest of the block upon. And you can see that sometimes the sketch doesn't show up if you're zoomed in too much, but then you can see it if you zoom out a little bit, but it is there. But now I also need to make like the crankcase, or at least within the engine block I also need to make the crankcase that actually allows it to rotate in there. But why doesn't it show up right now? And we know that the crankshaft was 70 millimeters, so let's make that 80 right now. And also let's select maybe 90 to make like the outer barrel for it. And I'm not sketching it, and you can't really see what is happening. Sometimes in assemblies, stuff like that kind of, happens a little bit, but with experience, you'll find that it's kind of still going on the way you kind of expected it to. Let's see from which angle I could do this best. I think so. Something like that, and cut it in half, and then from now on the sketch will probably remain in position. And that's basically like the first step. So this is the first like half of a cylinder, half of a pipe, I guess, that we're gonna make. And let's say it is about 100 millimeters. I think the crankshaft was as well. So that would be from wall to wall, perfect. And then we would have, let's cap the crankshaft in place immediately. So then we can select this line, convert entities, and then also select this cylinder right here. And then click on and then we're gonna extrude that sketch for 10 millimeters inward. And we're gonna replicate the same on this outer surface. So basically convert entities on that sketch, I guess. And now we have the first initial crankshaft casing for just the crankshaft itself to sit in. And now we're gonna also add the banks of cylinders to it. So we already know that this will be like the start point, and then there will be a bank right there, and then also a bank right there. And let's also make like a center line, and that kind of gives us the upward position. And then here we know we need to make it a 60-degree angle, but we also need to keep it modified or at least somewhat symmetrical. So we're gonna put it at a 30-degree angle there, and that will be like the initial shape of the banks first. But first off, what I kind of want to do is make sure that the pistons are properly aligned. And to do that, I'm gonna make the top of the connecting rod just a little bit wider, this circle initially. Let's say by 5 millimeters at each end. And then we can kind of position it and outline it perfectly with the pistons themselves. If I then select this wall, press mate, and push it up against that wall right there, then now you can see that the piston is perfectly aligned with the connecting rod. Okay. And now you can also see that this piston is kind of like portraying to the outside on this end, and the other one doing the same thing on the other. But we're gonna tackle that in a second. Select this component, edit component, and then I'm gonna make a reference geometry. And that is basically creating just one of these planes. So here you have front plane, top plane, right plane. You can create your own planes dedicated to sketches and stuff if you want to have like a sketch a surface that is perfectly perpendicular to this line. You can just select the outline that you want the surface to start there, and then you select the line itself, and then it will just create a perpendicular, like a perfect section to the actual line that you've drawn. And I'm gonna do that for this section, but I'm also gonna do that for the other one. And stuff like this you probably could mirror, but you know, better to just do it that way. Something like that. And now we have plane 1 and 2 that we can also sketch on, and that is what we're going to use to also create the actual cylinder banks for the motor. So here what we're basically going to do is from this surface we know that actually perfectly on this line as well, because it's coming straight from the center of the circle of the crankshaft, we will have the bank itself, and the bank will kind of need to be wide enough for it to support the 86 millimeter bore. So let's say 50 centimeters on each, 50 millimeters on each section. It will allow you to have a 86.03 millimeter bore, but I should divide it by 2 because that is the radius. There you go. And we also know that from the center of the block, if you actually look at where the connecting rods connect, so on of the center of the block, they actually have like a 15 millimeter offset to one side and the other for it to actually like start the section with the cylinder with. So from the center of the section to the center of this line, I'm gonna make a 15 millimeter offset. And as you can see, the dimensions kind of seem a little bit changing. So that is basically what that will be. And with this, you actually already know and what the dimensions will be of your entire block and everything, but we can still kind of add on to it. Let's say the actual cylinder wall is going to be 5 millimeters. So now that we have the circle that is outlining like the perfect position for the piston to operate from, we're actually gonna take this position and extrude cut, oh my bad, extrude boss base, take the sketch and use that cylinder and select up to surface, and then we're gonna select this surface right here to do so. And then we're also gonna do the same for the other side. But that's why I also think it's kind of good to make mistakes along the road, you know, because it kind of helps out to showcasing also what the problems might be to kind of that you will bump into. And now you can see it perfectly fits into positions and just falls into place. And also let's check one more thing, because I don't think we can move it around like that. Let's make sure that this one is upright. So we're gonna connect and make the engine block to the top plane from that bottom section. Let's see where it went to. Top plane, yeah. Now it kind of looks like it's sideways, but it will make sense as soon as I put it that way. And now we have like the engine block mated to the top plane, and I'm gonna just fix it in position right now so it just can't move. And then you'll be able to see as soon as I rotate the crankshaft that the pistons are moving up and down. But so basically what we want to do is to kind of keep it in its top position. So to do that, you can see here that we have this connecting rod, basically the plane for it. And what I'm gonna do is I'm gonna mate it to the engine block, the plane, so for it to sit perpendicular to that plane basically. So with that surface, the side of the connecting rod selected, I'm just gonna select that plane, and then because it is always kind of like within that position, it will kind of know to make it perpendicular. And in that case, now the engine won't be able to move at all because it will just maintain it from that level. And what we can do now is actually select the engine block first and click on edit components and click on this surface right here. Oh, I think I already found like an error that might be helpful for some of you to kind of see. But basically what you could do is select this surface, and click on sketch, but now it says that assembly 2, or this part is already like defined in assembly 2 or something. So we're gonna break that reference by going into the engine part. Sometimes if you're working with assemblies and other things and stuff, it can kind of get misconstrued and stuff. Or is it the engine block itself? I think it's the engine block itself that has the references. Yes, I think it is. So we can go into the engine block. The piston, I think, is free from references, but you can now see here that on this actual sketch there is a question mark behind it, and as soon as that is done, then it means that it's kind of using dimensions from another component in order to make this or build this. And you can just make sure to kind of break that reference so that you can still modify it and everything, but that it kind of maintains the same dimensions and stuff. So you can right click the sketch with the question mark behind it and click on external references, and then you can click on the reference itself, break selected, and then okay. And then as soon as that happens, then you will see a X instead of a question mark, and now you can modify this component in conjunction with others and stuff, you know. So that kind of works out a lot better for me. And then I can now again press on edit component. Now there aren't any pop-ups showing up that the part has some other references and stuff, and then I can select this surface, click on sketch, and basically draw a circle around everything. Or I could have just converted entities or something, but you know, whatever suits you. And then from here on out, I can extrude everything away. And then as soon as this is now done, you will see that this flush, that the top dead center of the actual piston is flush with the engine block. And now to kind of do the same on the other side, I could replicate the entire process, or I could just stay into the engine block itself and click on sketch and basically just look at what the reference dimensions would be and replicating, you know. So take this line 209.55 and then basically make a line right here. I'm not gonna dock it at the end because then the dimensions won't float, but then I can put that dimension in there, the 209.55, and then just make a line that kind of goes from here directly perpendicular to there. It might have been easier and faster to do it the way that I did it before, but that would have kind of gave me like one thing to show you, and I showed you like multiple ways to do the same thing. So I kind of think for the tutorial it makes sense to do it this way. And now I can go back into the connecting rod right here and take this perpendicular made out of it. And now you will be able to see that as soon as I rotate this one, it is also flush at the top dead center. So that is basically like the motion of the V6 already. And now, in order to turn this into a V6, I could do a couple of things. And the way that I'm gonna go about it is by selecting linear pattern. And with linear pattern, you can select this line, and then it will kind of within that direction of the line, it will just duplicate your entire design, you know. So here you can select if you want to have just features and faces of the design that you want to duplicate in a linear pattern, or if you want to just use the entire body. And in my case, it's going to be the entire body. And we also know that the distance between these connecting rods and everything, or the block from this face to that face to the end, is 10 millimeters. So we can place that at 100, or maybe 100 millimeters, I should say. But then also we're gonna be ending up with like 10 millimeter wide spaces for the crankshaft to sit in, and I think that is a little bit overkill, so I can make it a little bit more narrow, like 95, so that they have some slight overlap between the two. And maybe, yeah, I think that would be perfect actually, to then also have like the housing and everything for the water and stuff. And then basically that's it. That's like your first initial V6 motor block. So basically now we have the V6 engine lined up and everything. The only thing is that they aren't like intersecting components. They haven't merged it. They're just kind of like loose separate entities, I guess. And if you want to change that, you can open the part again, and then go into intersect and then select these different entities, and if everything is good, then it should just be all right to do so. And now you have a complete engine block. But that is kind of like the fun part of doing it this way, because you'll eventually have like a very modular engine block in a sense, to where I could just make this into a V12 if I wanted to by just pressing this to 6. That is just creating 6 instances of the same piece, you know. So that makes it very modular, and I think as a start, it's a good way to kind of go about it. To also for yourself kind of figure out how you want to do that and how you want to replicate things like that. So basically, I'm just gonna take one more step, and that is I'm gonna cut out these holes, and then I'm gonna add like the crankshaft length to it to actually fill the entire block, put all the pistons in there, and then we're gonna take it to the next video from that point forward. So here we're gonna use convert entities, select these inner surfaces, and also I'm gonna select this line right here because I don't want it to cut a hole through the entire thing, for that case at least. And then we're gonna select the cut extrude, but not through all, but up to surface, because I only want them to cut up through here and not continue on beyond that wall, I guess. Like so. And then you'll see those holes lining up. If there's a wall or like a hole here or something, it's not like the end of the world if that would be still there in the real world, because there won't be like any gas exchangers, anything happening between those pistons or the cylinders. But probably I will close it off at some point, but we'll find out later whether that will be the case. And then kind of replicate the same process over here. So that was basically your first engine block, and we can already like 3D print this, and we could you know place it like on one of the slicers and stuff, and that would already be like sufficient to kind of see it in motion and everything. And here you can kind of if you then also lock the crankshaft again in place. I think when we intersected it, it didn't recognize that part anymore. So now it is in place. I can also make this kind of like see-through, then change the transparency. Oh, that sucks. Why you won't be able, usually it would kind of showcase all of the moving components, I guess, in that mode. But at least we have something going for ourselves. And then we actually need to replicate this section again, but there is like slight variations that we need to make to it in order to actually fully make it functional. My bad. I am going to linear pattern this, because I actually do want to actually maintain the same dimensions and the flexibility and everything, but we're gonna make some slight changes to it. The direction should be so we actually need to make it like 95 millimeters going into that direction. So we're now gonna select the top plane, not the top plane, which one was it? Front plane, to actually pattern it also into that direction, 95 millimeters apart, same dimensions as the crankshaft, or as the engine block, I should say. So that should just fit automatically. But again, you know, it wasn't intersecting components. Is there a way to do that in the linear pattern actually, to actually make them merge on instance? Ferry sketch, full preview, instances to ferry. I don't know. I don't think there would be. It should be like right in here. It usually kind of selects merge or something, but you know, we'll figure that out another time. So then we actually need to like merge these together first. It doesn't necessarily need to be done first or anything, but we'll just kind of do it with the intersect tool. So then you go to intersect and you just select all the 3 components. Yes, but there's one thing that's kind of like not the way it should be, and that is that we don't need to have the connecting rod lobes on the crankshaft at the same position 3 times, because that will just allow you to have like a you know just on 1 or 2 positions at the combustion stroke. You will just have a combustion instead of at every like 120 degrees. So what we're gonna do is we're gonna select this surface, cut extrude, convert entities, cut extrude up to this surface right here, and then keep all bodies, of course, and then go ahead and do the same here. Cut extrude, keep all of the bodies, and then what we're gonna do is we're gonna select this sketch, and we're gonna convert entities for this one, and then we're gonna select not move entities but rotate entities, and we're gonna rotate it from this point. The rotation is going to be this origin point, and we want it to rotate 120 degrees up to that point, and that is basically how you do it. And then we're going to take that again and then select up to surface, up to that surface right there, and then we're going to replicate the process. So we have one here, and then also one at the top. So again, extrude from that surface, and take that entire sketch, click on convert entities, and then again rotate entities. The entities you want to rotate is this connecting rod lobe right there, and the center of rotation is going to be right there, and then again 120 degrees, and then it moves to the top position where the others aren't. And then again, extrude boss base, select the line up to the surface, select the surface, done. And regularly in crankshaft, you will also see like sketches a little bit more drawn where maybe let's say if I take it up to here, that from the side especially, that they basically have somewhat of a shape that can kind of take this lobe into consideration, but then excludes most of the mass that you don't really need from it. So if you would then like draw a circle to the outer line, 35, and then make like a cube tooth, somewhat like that, and then cut it out. That is usually kind of like the shape that you see more on a crankshaft, where you have like some balancing weight on the opposite end of where the connecting rod would actually be. But we're gonna get into that detail into the next videos. But just to kind of give you like a hint of what we should expect and why it maybe doesn't yet look like a crankshaft to you. But this is just like a very rudimentary basic shape of what a crankshaft kind of should entail and have dimensionally. And then from this point forward, and the final thing that we're actually going to do in order to make everything function the way it should is to actually make sure that the pistons and the connecting rods are also in position on the other places. And the way we're going to do that is by dragging over it. Also, if you drag from left to right in SolidWorks, then you're only going to select the components that are fully in the box. But if you select from right to left, then also if it's just slightly within it, it will get selected. So that is also a good way to kind of select what you need and what you don't need. So if you want everything, you can select from right to left and you have a green box. If you don't want to select everything, but you just want to select what's in the box, you select from left to right, and then it will just highlight it in blue what you will select, you know. So then from here, we click on Control C, Control V. And then you will see that we'll have another set of like connecting rods and pistons here, and then from here we can connect those to the actual connecting rod lobe on the crankshaft, and then also put them into position when it comes to the placement and stuff. And then for the final part, we're actually also going to align them with the actual engine block. Concentric. Okay, they are kind of like correctly in position, but they just need to be aligned with the engine block itself. And then we're going to do the same for the final position. I'm going to make these directly to each other, so they kind of stay in position. And then as soon as I made them to this one right here, it should just move in place. And then just place them against the side of the wall, bam. And then for the final step, we're going to showcase the engine block itself, and then made it with the pistons. And now, if we hide this engine block, you should be able to see all of the pistons move in the way that they should. And for me, this is always like a fun eureka moment where you just see all of the work kind of come together, and you were just making a bunch of random components and parts. But this is truly, and it really is the start of the whole industrial revolution when it comes to steam engines, when trains and things became into play. Instead of having like a fuel mixture that you would place within a cylinder like this, you would have pressurized steam. You would have pressurized steam that would actually be pushing the pistons up and down to actually set like pressurized motion into kinetic motion, which then becomes rotational centrifugal motion and everything through the crankshaft and connecting rod, a cylinder and system setup, you know. So it's fascinating to me that people could come up with these type of solutions before computers even were a thing, you know. Like that's mind-boggling to me every single day, to kind of see what was possible and also what is still remaining, you know. And from here on out, we're just gonna add like levels of complexity, you know. So that was basically it for the first episode. This is like my excitement when it comes to designing, where you can just create stuff where it's just, I don't know, it's a lot of fun to me. I don't know, I feel like a very free individual when I get to do stuff like this. Maybe a quote that is recognizable for people: power is the ability to define phenomena and make them act in a desirable manner. And I think that this is truly like one of those tools and the things that you can use and utilize to your best ability, and then kind of make whatever phenomena you want to make come to life and into existence, make reality, you know. So to me, it's truly like a form of power to be able to do this, and it feels extremely good to me. So I'm gonna get into editing this video. Hopefully you like everything that you saw, and you were capable of kind of like following along to the process and everything that I did to kind of get to there. In the next video, we'll be adding some systems to this engine. So we will make a dry sump oil pan. We will make some cooling circuits for the water to kind of go around. We will make some jets where like lubricants and stuff will be able to flow through, and also some attachment points for some other stuff. And then from that point forward, we're gonna make the cylinder heads in the third video. And with the making of the cylinder heads, we might make some auxiliary like air intake and exhaust pipes and stuff, maybe in a fourth video, maybe even in the same video. I'll see in a second. And from there, we're just gonna design like a full car around. I'm not gonna go into the details of the gearbox right now because I want to go into the chassis and stuff like that a little bit sooner than I kind of anticipated. But we can do that like in a later stage of the video process and everything, to still make sure that we have like a complete car at the end of the series. But for now, I think that was it. I'm gonna end it there. Thank you for watching. Please leave a like or subscribe to Veldboom Studios on all forms of social media. We'll be here to leave a mark in 2025. Please believe it when I say so. And eventually you will actually see these parts and cars and stuff come to life, as we will also 3D print a whole lot of it and see if we maybe can have some actual metal components also being built for our own motors and stuff. We'll see. Thank you for watching. Please leave a like, subscribe. Like I said, my name is Veldboom. I'm out.